You have 4 minutes. That is not a metaphor, that is not an exaggeration. That is the actual calculated amount of time a human being would have before their body begins to fail on the surface of Io, one of Jupiter's moons, and by every measurable scientific standard, the most geologically violent world in the entire solar system. Not Mars, not Venus, Io. And the reason why is far stranger than anything Hollywood has ever imagined. Io is the 4th largest moon in our solar system. It orbits Jupiter at a distance of roughly 422,000 kilometers, close enough to be locked in a gravitational war it can never win. From a distance, it looks almost peaceful. Scientists once described it as resembling a pepperoni pizza, bright oranges, yellows, and reds scattered across its surface. But that color is not rock, it is not soil, it is sulfur. Thousands of tons of it, constantly erupting, constantly reshaping, constantly burying every inch of the surface in a world that never stops destroying itself. When the Voyager 1 spacecraft flew past Io in 1979, scientists expected a dead, quiet moon. What they found instead shook the entire field of planetary science. Io was alive, violently, uncontrollably alive. And decades later, we are still uncovering just how extreme that reality truly is. Here is why this matters beyond pure scientific curiosity. Humanity is planning to send people deeper into the solar system than ever before. Mars missions are being actively developed. Deep space exploration is no longer science fiction. It is a timeline. And as we push further out, the moons of Jupiter are not just interesting side notes, they are destinations. Europa, one of Jupiter's moons, is considered one of the most promising places to search for extraterrestrial life. Any mission architecture heading to the Jovian system will pass through a region where Io's influence is felt across millions of kilometers. Understanding what makes Io so lethal is not just academic, it is preparation. Because the forces that make Io unsurvivable are the same forces that will define the risks of every deep space mission humanity ever attempts. And there's something else. Something scientists discovered recently that suggests Io may be even more extreme than we previously understood. A discovery that changes what we thought we knew about volcanic worlds entirely. To understand why 4 minutes is the upper limit of survival on Io, you need to understand what is actually happening on and beneath its surface. Io is caught in a gravitational tug-of-war between 3 massive bodies, Jupiter, Europa, and Ganymede. These 3 pull on Io from slightly different directions as they orbit, and that constant pulling and stretching creates something called tidal heating. The interior of Io is being physically kneaded like dough, and that friction generates enormous amounts of heat deep inside the moon. The result is the most volcanically active body in the known solar system. Io has over 400 active volcanoes. Some of them are erupting right now as you watch this. Its largest volcano, Loki Patera, is a lava lake so vast it would stretch across the entire state of Maryland. Eruption plumes on Io have been observed reaching heights of 500 kilometers above the surface. That is nearly 60 times the height at which commercial aircraft fly on Earth. The surface temperature near active vents reaches over 1600 degrees Celsius. That is hot enough to melt iron. But here is what makes Io uniquely lethal beyond just the heat. Io has almost no atmosphere. What exists is a thin, unstable shell of sulfur dioxide gas, and it collapses entirely when Io passes into Jupiter's shadow. The surface pressure is less than 1 billionth of Earth's atmospheric pressure. There is nothing to breathe, nothing to insulate, nothing to protect against what Jupiter does to anything that enters its magnetic field. For decades, scientists tracked Io primarily through flybys. Voyager gave us the first shock. The Galileo spacecraft gave us years of detailed observation in the 1990s and early 2000s. But it was the Juno mission, originally designed to study Jupiter, that began changing our understanding in ways no one fully anticipated. As Juno extended its mission and made close passes of Io beginning in late 2023 and into 2024, its instruments detected something unexpected. The heat signatures coming from Io's surface were far more widespread than volcanic vent locations alone could explain. Large sections of the surface between known volcanic sites were radiating heat, suggesting that the internal magma systems are far more interconnected than previous models assumed. In simple terms, it is not just that Io has volcanoes, it is that Io's entire crust may be sitting on top of a near global ocean of magma. The surface, every single inch of it, is essentially a thin shell floating above an ocean of liquid rock. The James Webb Space Telescope has also contributed. Its infrared sensitivity allowed scientists to observe Io's thermal emissions with a level of detail never previously possible from that distance. What came back confirmed the Juno data and added something more: thermal hotspots appearing and disappearing on timescales of hours, suggesting eruption cycles far more rapid and unpredictable than anyone had modeled. Io is not just violent, it is chaotic in ways our instruments are only beginning to resolve. But here's where it gets complicated. Some scientists are pushing back not on whether Io is extreme, but on the global magma ocean theory itself. A competing group of researchers argues that the heat distribution data can be explained through an alternative model, one involving deep branching networks of magma channels rather than a continuous underground ocean. Why does that distinction matter? Because if Io has a global magma ocean, it represents something we have never confirmed anywhere in the solar system. It would make Io not just an anomaly, but an entirely new category of world, a magma ocean planet, something theorized to exist in the early solar system billions of years ago when everything was still forming. There is also the question of Io's poles. Juno's close passes revealed that polar regions of Io appear significantly cooler, almost eerily so compared to the equatorial chaos. Scientists are not sure why. One hypothesis suggests localized variations in tidal heating. Another suggests something more unusual, that the poles may be experiencing a form of geological quiet cycle, building pressure that releases in periodic mega eruptions. We don't know, and that uncertainty is scientifically significant. The implications of what we're learning about Io reach well beyond Jupiter's neighborhood. Tidal heating, the mechanism driving Io's insanity, is now understood to be one of the most powerful geological forces in the universe. It's not unique to our solar system. Astronomers have identified dozens of exoplanets orbiting close to massive gas giants or binary star systems where tidal forces would create conditions similar to or even exceeding what Io experiences. These are called tidally locked or tidally stressed worlds, and they exist throughout the galaxy in enormous numbers. Io is essentially a laboratory. Every eruption, every thermal reading, every mapped lava flow is data that helps us understand what billions of other worlds across the cosmos might look like. Understanding how long a crust can hold before it breaks. Understanding how volcanic outgassing shapes or destroys atmospheres. Understanding what the early Earth might have looked like, because current evidence suggests our own planet went through an Io-like phase roughly 4 billion years ago. There's also the radiation dimension. Io orbits within Jupiter's most intense radiation belts. The surface receives radiation doses approximately 3,600 times the level that would be instantly fatal to a human being. Even a spacecraft designed to withstand deep space conditions degrades measurably during close Io encounters. Juno's instruments showed radiation-related wear from its recent passes. This is what makes that 4-minute survival window not pessimistic, but optimistic. Radiation alone, without any volcanic activity or temperature exposure, would be immediately lethal. The estimate accounts for a protected suit and assumes landing far from any active volcanic region. In reality, given what we now understand about the subsurface heat distribution, there may be no safe landing zone on Io at all. So what does this mean for humanity's actual future in space? The Jovian system is not an abstract destination. NASA's Europa Clipper mission, launched in 2024, is currently en route to Jupiter and will conduct dozens of flybys of Europa, studying its ice shell and subsurface ocean for signs of habitability. Europa Clipper will pass through the same radiation environment that makes Io so hostile. Every engineering decision on that spacecraft was shaped in part by what we learned from studying Io. Future crewed missions, if they ever target the outer solar system, will face the Io problem directly. Any trajectory to Europa or Ganymede requires navigating Jupiter's radiation belts. Understanding those belts, how they fluctuate, how Io's volcanic activity feeds charged particles into them, is mission-critical knowledge. There is also a more immediate consideration. Io demonstrates with brutal clarity that habitability is not simply about distance from a star. It is about the entire gravitational and electromagnetic environment a world exists within. A planet can be the right temperature, it can have the right chemical composition, and it can still be utterly, completely hostile to life as we know it. That changes how we evaluate worlds beyond our solar system. It complicates our search for life, and it forces a more honest reckoning with what survival in the universe actually requires. Zoom out even further, and Io begins to look less like an exception and more like a reminder. The universe is not designed for comfort. The same forces that create structure also create destruction. The same energy that ignites stars eventually consumes them. Across the observable universe, 93 billion light-years containing an estimated 2 trillion galaxies, Io